Hi, I'm Tommy Unger, a PhD student here at BU. I'm here to talk a little bit about some mechanisms that we've been building to do address space caching and using them to accelerate a functions as a service or serverless platform. This work is in collaboration with my co-conspirators James Cadden, Han Dong, Yara Odd, my advisor Jonathan Apavu, and mentor Ron Krieger. All right, so here's a architecture diagram of a function as a service platform. And the idea here is that our clients can upload their high-level source code into the platform and then request that it gets executed on some input. And the clients can make these requests whenever they want. It's up to the platform to move them through to locate the code that's going to run, get it out to an invoker, and run it somewhere that's isolated and able to meet the performance goals. Those outputs percolate back out of the system to the clients. There's a number of challenges for this system. One of them is creating those isolated execution environments. And in a mutually distrusting scenario, that's going to be one of the major challenges. The other one is if these are high-level scripts that we're running, there's a lot of overhead to getting these execution environments up. And we're going to try to see if taking a different take on this problem, we might be able to solve both of those problems at once. All right, so here's a motivating result that we have of one of these production functions as a service platforms. This is backed by container-based isolation mechanisms. And what I'm showing you is a sequence of runs of 8,000 function executions. What's going on, what we're varying on the x-axis is a pool of unique functions that we're running. So of a pool of this size, we run 8,000 function executions. And what you see is as you increase the size of that pool, and so you're pulling more unique functions down to execute, eventually the run times to get through that set of function executions starts blowing up. And we're going to argue through this talk that if you're able to create really lightweight execution environments, and with a few tricks, we're going to be able to make a lot of progress on this. To put a point on the problem, these container-based approaches are really bottlenecked on their creation. The creation of a container, it's about 1,000 times longer than process creation. So if you want to simulate this at home, just put a spin loop and fork and let it spin for a second before you get a new execution site. So taking a little look at some of the possible places you could start to rebuild this, to build up a system, you could think about starting with a process, right? Processes are fast to get you an execution environment, but because of their large system APIs, we don't consider them very isolated. On the other extreme are virtual machines. These take like a minute to boot, but once they're up, we have pretty high confidence in their isolation. The de facto standard for these services is the container. It's something of a compromise between them. They take about a second to create, but once they're up, we have those cool namespacing properties of Linux containers to provide a little more isolation. So things are a little bleak right now, but there's a lot of cool research directions. Some of them are taking those more isolated environments and trying to push them out to become more performant. But the one that we're going to be talking about and building on top of takes the process and tries to drag it along that isolation axis. So we're gonna base our work on top of this. Real quick, we're going to jump back to Ali's unikernels, right? So standard processes, we have applications running on top of a kernel. Ali told us about how you can embed an application inside a single address space with all your system components and the benefits that it can bring. So just to gesture at the isolation properties here, the idea is that we're running multiple applications across multiple unikernels on top of a truly minimal unikernel monitor. So the idea here is that if you can corrupt the network stack, you only break your own network stack. You're not actually potentially getting information from another user. The other thing to notice here is that as all of your system resources are collected into one space, you're able to resolve almost everything the application can ask for inside there without needing to have any rich interface down into that monitor. So the goal for this work is taking that unikernel approach. Can we close the performance gap to actually make this an expressive model where you can do real function composition, non-trivial fan out and fan in execution? So the key observation here, and we can thank Aaron for this, is, hey, take a look at that unikernel address space, right? If you wanted to take a snapshot, if you wanted to make a copy of it and throw it in a cache, everything's there for you to do it, right? Consider the alternative where you're trying to snapshot an application and you have to go down into the kernel and grab some file system state and do a bunch of work to make that cached entry. So here's the idea behind that snapshot caching. So consider the lifetime of one of these high-level language environments, right? So there's a whole bunch of steps, and some of them are particularly expensive. But what I want you to think more about is the spectrum of a very generic execution environment down to a very specialized state. And what we're going to be looking at is, are there particular points along the way that make a lot of sense for making a cached entry that you might be able to use when you re-execute these functions. So let's walk through a couple different use cases, right? Your client comes along and says, hey, remember function f? Why don't you go run it on x right now? So in the worst case, you're going through this cold start path where you have to create everything. You have to bring up your interpreter. That can be expensive. You have to receive function code. You have to do imports and compilation steps. And what we're suggesting here is, hey, after you get that interpreter up, why don't you take a snapshot so anyone else who wants to run function code in that language can just pull that down from the cache, inject their function code, compile, and run. And that's our warm start path, is you already have your language-specific interpreter up. In the best case, you've seen this function f before, and after compiling it to bytecode, you took a snapshot and threw it in your cache. Now when you see invocation requests, hey, run this on Y, on Z, you can just throw them in and execute forward. So to profile this and to actually get an idea of it running in the real world, we took an existing function as a service platform, OpenWhisk, and we chopped off the backside of it, this container-based solution, and we retrofitted our home-baked distributed library operating system on to see what would happen with taking advantage of those snapshots. So now I'm showing you the same results. The blue line you saw before, that's the container-based execution path. And down below is what we're seeing using our snapshotting mechanism. And what goes a long way to describing the difference between those graphs is the cache miss latencies. And so what you're really seeing here is on the red line in our approach, really our worst case is already having a language-specific interpreter up and ready to run, and just executing forward from that point. Whereas on Linux, your worst case is you need to sit down for a second, create a container, and run it. I'm not even mentioning that the container destruction paths are equally or more expensive. So some of the current work here, well, one thing is actually making good on making these multi-node backend invokers, but other things are adding performant I/O, increasing our hardware isolation properties, and building tools for actually profiling and understanding this better. Some of our future directions here, the first 4 points here, I think it's kind of neat that they're all based on that snapshot primitive. And so we're thinking about building distributed snapshot caches, about doing things like dynamically linked libraries on multiple snapshots, overlaying them together, copy on writing and executing forward, and then exposing this primitive to users so that they can implement their own memoization, their own caching, and also maybe implementing things like snapshotting and rolling back. So a lot more than I could fit in a 10-minute talk, but thanks for coming.